Welcome Statistics 1 students to week 12 of maintenance. We're introducing a new topic in today's maintenance, which is permutations and combinations. So we've done a little bit of this in class, so hopefully you'll be prepared for what's coming there. The first question is a representation of data question. It's coding. And Swati measures the lengths of 18 stick insects, finds that sum of x squared is 967, and that the mean length is 58 over 9, and we've got to find this value and this value, the coded values. So what I'm going to do first is I'm going to find out the variance of the uncoded data, and the variance will remain the same because you can see we're just moving everything to the left by 5, so the variance or the spread is going to remain the same, really, isn't it? So the variance will be equal to the sum of x squared over 18 minus your mean squared, and that gives me a variance of 1975 over 162. And we know therefore that the variance of the coded data is going to be the same, so we know that the sum of x minus 5 all squared over 18 minus the coded data's mean, and that is going to be 58 over 9 subtract 5 because everything has moved by 5, so that's the new mean, and that ought to give us the same variance as the uncoded variance. And we just rearrange this and we find that the sum of x minus 5 all squared, if we rearrange this correctly, excuse me, I'm getting a 257, and then I can also find, so that's that one done. Now what about this one here? Well, I know what the new mean is, and I get the mean by doing the sum of x minus 5 divided by the number of items of data, and that gives me this new mean of the original mean, take away 5. And therefore, if I just rearrange that, I get the sum of x minus 5 being equal to 26. And that is indeed the answer. Okay, so the next one, following houses prices are in thousands of dollars, arranged in ascending order for 51 houses from a certain area. We've got to draw a box and whisker graph. Okay, well, since there's 51 houses, we know the median is the 26th item of data. So for this, all you need to do is go 51 divided by 2, and that gives you 25.5, so 26th item of data. So if there's 17 across, which there is, 18, 19, 20, 21, 22, 23, 24, 25, 26, this must be our median. The lower quartile is going to be the 51 times 0.25, so we're looking for the 13th item of data. And so that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is lower quartile. And the upper quartile will be 13 above the median. So 0.75 times 51, it's giving me the 39th item of data. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think it's 690. That's the upper quartile. And then we're ready to draw our stem and box and whisker. So I'll make that 200, 300, 400, 500, 600, 700, 800, 900, 1000. And our lowest value is 253, so I can pop that about there approximately. And we know that we've got a lower quartile of 520, so 520 is about, well, each of these is worth 20, isn't it? So 520 is here. So we can join that up to there with a straight line. Of course, you guys are going to use a ruler. And then we've got a median at 554, which is approximately here. And then we go all the way to 690 for our last one. So that's halfway between there. Join that up there. It's a bit of a horrific box, but you get the general idea. And then we go all the way up to 986, which is our highest value. Should be about there. Okay, so there's my box and whisker plot. Now, the next question is: an expensive house is defined as one that has a price of more than 1.5 times the interquartile range above the upper quartile. So we've got to now define which ones are the expensive houses. So 690, a takeaway 520, will give us the interquartile range. So that's 170, and if we multiply 170 by 1.5, we get 255. And so we're going to add 255 plus the upper quartile, and that gives us 945. So anything that's above 945 is going to be defined as an expensive house. So the prices of the expensive houses are 957,000 and 986,000. The one disadvantage of using a box and whisker plot rather than a stem and leaf diagram. Okay, so you don't see the individual pieces of data. Okay, so that's probably what they're looking for there. Now, the next one, we're looking at people living in two different towns, Mumbok and Bagville, and they're classified by their age, and we've got the numbers in thousands living in each town, as shown below. One of the towns is chosen. The probability of choosing Mumbok is 0.6, and Bagville is 0.4. Then a person is chosen at random from each town, from the town that you chose. And here's the thing: given the chosen person is between 80 and 60, find the probability the chosen town is Mumbok. So essentially what we're trying to find is the probability of a Mumbok given we chose the 18 to 60 year old age group. Now the way we do this is, well, what's the probability of Mumbok intersecting 18 to 60 year olds, and we divide that by the probability of 18 to 60. Now, the probability of M intersection 18 to 60 is, well, chance of choosing M is 0.6, and then out of that there's 55 18 to 60 year olds out of a total of 50, 75, 80, 90 I think. And then we're going to divide that by, well, one way of getting those 18 to 60 year olds is if you choose Mumbok, but also the other way is choosing Bagville, which is 0.4, and there's 95 in that age group out of a total of 160, I think. Let me just quickly correct that, that looks a bit messy. 160. Now, if you chuck that into your calculator, I get 88 over 145. So, oh, what a hash up. 88 over 145, and another way of saying this is 0.607 to 3 significant figures, and that's indeed the answer. Okay, the discrete random variables question for the week. James, good old James, he's got a fair coin and tetrahedral numbered 1, 2, 3, 4. He tosses the coin once and the dice twice, and the random variable is defined. If the coin shows a head, then sum the scores. If the coin shows a tail, then X is the score on the first throw. Explain why X equals 1 can only be obtained by throwing a tail, and that it's 1/8. Okay, well, you must count 2 scores if you throw a head. Therefore, the lowest value you could get would be 2. With a head could be 2. Now, show that the probability of getting a x equals 1 is 1/8. Well, 1/2 for the getting the tail, and then 1/4 for getting the 1, and that is equal to 1/8. So that's nice and easy. Now, the next one, we've got to fill in these gaps here. So 2. So how do we get 2? Well, we could get heads and then 1, 1, or we could get tails and 2. I think those are the only options. Now, the first option, we can say that's like 1/2 for the heads times 1/4 for the 1 times 1/4, or this one here is 1/2 times 1/4. And we add those together. So 1/2 times 1/16 plus 1/2 times 1/4 gives me 5/32, 5/32. Now with the 4, we could get heads 1, 3, heads 3, 1, because we can do that 2 ways, right? Heads 2, 2. I think that's it from the heads, and then tails 4. I think those are the only options. Now, each of these ways, right, is the same. It's 1/2 times 1/4 times 1/4. And since there's 3 of them, we can just times that by 3. And this one here is 1/2 times 1/4. Now we add that all together. And I'm getting 7/32. Now with this last one here, this 6 business, you could get heads 4, 2, heads 2, 4, heads 3, 3. And that's the only way you could do this. Now there's 3 lots of the same thing here. 3 lots of 1/2 times 1/4 times 1/4. And so that gives us 3/32. Now the last part of this question is, event Q is James throws a tail, event R is the value of x is 7, and we've got to determine whether Q and R are exclusive. And the answer is yes, they are exclusive, and the reason for this is there is no way you can get both of those together. You can't get a value of 7 if you throw a tail, because the highest value you could get would be 4. Okay, the last question of the day, permutations and combinations. The shop has 7 different mountain bikes, 5 different racing bicycles, and 8 different ordinary bicycles, and the club is selecting 6, and we've got to find out how many selections could be made. No more than 3 mountain bicycles, no more than 2 of the other types. Okay, well, if we go 3 mountain bicycles, so we could go mountain bikes 3, racing bikes and ordinary bikes. Well, if we go 3, then we could go 2 here and 1 here, I think, because we've got to get 6, don't we? So if we go 3 mountain bikes, 2 racing, or we could potentially go 3 mountain bikes, 1 racing bike, 2 ordinary bikes. No more than 3 mountain bikes, so we could go 2 of them, in which case we'd have to have 2 of the others. And you can see Therefore, there's no way we can have just one mountain bike because we're only allowed 2 of the other type, and then we wouldn't be able to get 6 bicycles that we need to buy. So here's our different options. The first option, we're picking from a group of, how many mountain bikes? 7. So it's 7, choose 3. So we want to choose 3 from the 7 different mountain bikes. Then we want to choose 2 from the 5 racing bikes. So 5, choose 2. Then we want to times 8, choose 1, because we're choosing one of the ordinary bikes. So that's the first one. Then we're going to add to it this next option, which is 7, choose 3. So we want 3 of the mountain bikes times 5, choose 1, because we only want one of the racing bikes this time. And then times 8, choose 2, because we want 2 out of the possible 8 ordinary bikes. And then finally, the last one is we're choosing 2 from each type. So 7, choose 2, times 5, choose 2, times 8, choose 2. Now when we chuck this into our calculator and add it all up, so 7, choose 3, times 5, choose 2, times 8, choose 1, plus 7, choose 3, times 5, choose 1, times 8, choose 2, plus 7, choose 2, times 5, choose 2, times 8, choose 2. When you add that all together, well, I'm getting 13,580 different selections that we can make there. Well, I hope that's been helpful to you. I hope everything's making sense, but if not, please let me know. If I've made a mistake, let me know. Alright team, God bless.